Hey folks, how's it going? This is Mr. Murray coming to you with a recap video for Course 1 Honors. And this little recap video is for the exponential functions practice that we did. And that was assigned on Wednesday, May 13th, 2020. Okay, so in this video, I'm going to be walking through the ideas behind how we set up the graphs, how we do the key analysis items, and kind of talk about stuff that you really want to make sure you take away from this. All right. So the first thing, and I really have tried to make a strong emphasis on this all year, is that you should never forget to make a table. Okay, that's really important. Throughout high school, you're going to come upon different types of functions. Next year in course 2, you might talk about square root functions, cube root functions, different kinds of polynomial functions. In junior year, I'll talk about trig functions. If you can get in the habit of setting up a table and plugging in numbers, that will help you develop the graph no matter what kind of function you're dealing with. So that's why it's really important to think about getting in the habit of doing that now. In this worksheet, I've gone ahead and made a table on the front and back side. In the front, it's on the bottom, and on the back, it was on top of the graph. Okay, so to get started, we're going to go ahead and make a graph here. Now, what we know is that any exponential function will follow this form. F of x equals a times b to the x minus h plus k. Okay, and some intuition we've developed is that if a is less than 0, we are below the horizontal asymptote, and if a is more than 0, we're above it. So when I graph this function out here, I'm going to expect for it to be above the horizontal asymptote. Furthermore, remember the b value tells you whether you're getting further from 0 or closer to 0. When b is greater than 0 but less than 1, you're getting closer to 0. But when b is greater than 1, you're getting farther from 0. Okay, so let's take a look at what that looks like here. So I'm going to start by setting up my graph at my table, and unfortunately I got to do it down here. So I'll start by plugging in 0. Now remember, anything to the 0 is always 1. So a third to the 0 is 1. 1 times 45 is 45. Okay, now I come back. I plug in 1. A third to the 1, anything to the power of 1 is itself. A third to the 1 is therefore a third. Times 45 is 15. Now you may have noticed at the top of the sheet, I said, only plot what is on or close to the graph. So the first 2 points are not on the graph, 45 and 15. They're not on the graph and they're not close. If it was 10.5, if it was 11, okay. But we're not really in that position. Okay, so we go to 2. As we can see, we're going in that direction. So we plug in 2, we get a third squared. And I'm going to come up here to show you that. A third squared is equal to a third times a third, which is equal to a ninth. And 1/9 times 45 is the same as 45 divided by 9. And 45 divided by 9 is 5. So hopefully you see a pattern here. Observe that as x goes up by 1, I divide by 3. Then I divide by 3. And if I keep going, the same pattern emerges. So what's cool about this is that you can use some of the cool stuff that we learned about when we talked about geometric sequences to also quickly find the output of an exponential function without plugging in and having to work with really big exponents, which can be difficult to do. Now I need to take a look at some negative numbers. But I note that if I'm at 0, I'm already off the graph, so I'm not going to actually need to do those. So my points were 0.45, which will not fit, 1.15, which will not fit. Okay, then I had 2, 5. I had 3 5/3. Now 5/3 is about 1 2/3. And then what I end up getting is a graph that looks something like this. So it's steep. It's really steep. And then it starts to come down and get real nice and close to 0. Okay, as x increases. So let's take a look at this graph. What do we notice? Well, the domain is negative infinity to infinity. You can plug anything in. What are the y values? Well, what you hopefully see is that they're getting very close to, but are never equal to 0, right? So we would get 5/9, 5/27, 5/81. No matter what happens on the denominator, the numerator is always going to be 5. But since the numerator will never be 0, the value of the fraction can never be 0. So therefore, we can never include 0 in the range. That's why we use the parenthesis. Then we can see the outputs are above 0 and the arrow points up. So we can see the range should be 0 to infinity. Okay, where is it increasing? So from left to right, we're always going down. So we're increasing nowhere and decreasing everywhere. Increasing nowhere and decreasing everywhere. Okay, where is it positive and negative? Here, it's positive everywhere, actually. Okay, because the values are always greater than 0, the y values, and it's negative nowhere. X-ints, there are no x-intercepts because the range, we can see it never reaches 0. And the y-intercept, as we saw earlier, was 0, 45. You're not always going to be able to see the y-intercept on the graph. And so if you can, you just use the graph. If you can't, you will need to plug in 0, find the output, and state it as a point. Okay, horizontal asymptote, as you can see, there's no plus anything off to the right of the function formula. And we can also see based on the graph that we're going to y equals 0. And finally, end behavior. As x goes to negative infinity, what's happening to y? Well, it's shooting up, right? F of x goes to infinity. And now as x goes to positive infinity, f of x is approaching, it's trying to become 0. All right. How about transformations from the so-called parent function? So for any given function, the parent function is just, imagine you just take the b value and you just do the x. That's going to essentially be our parent function. So our parent function looks like this. Okay. And it shoots up pretty high and then it comes on down. Okay. So here are some transformations. The main transformation here is that there has been a dilation. And the dilation is by a factor of 45. Now, if you think about it, if I had a 1/3 to the power of x, what you're essentially doing, the difference between this function, the black, and this function, the blue, is that the outputs of the blue function are the outputs of the black function, but you've multiplied them by 45. But if you multiply them by 45, you're going to get them a lot farther, right? They're going to farther from 0, right? They're going to become a lot bigger. So instead of getting 1, I'd get 45, right? Instead of getting 3, I'd get 135, right? I get a way, way, way bigger number, a number way, way, way further from 0. And so that's going to have the effect of dilating or stretching or pulling up that function. All right, so please make sure you understood what I did here, and then in a moment I will go ahead and move on to the second problem. All right, here we are, folks. So in the second problem, I actually put the table right on the graph, and I was able to do this because I had done this graph out ahead of time, and so I knew where the function was actually going to be. So I apologize if it was unclear here. It's negative 1/2 times 2 to the x plus 1 plus 2. Okay, so let's take a look. So here you see it's to the x plus 1. So what I'm going to do is I'm going to have my first one be negative 1. Because when I plug in negative 1, it makes the exponent 0. So 2 to the 0 is 1. Negative 1/2 times 1 is negative 1/2. Negative 1/2 plus 2 is 1/2, right? Negative 1/2 plus 2, positive 1/2. Now maybe I'll plug in 0. If I plug in 0, I get 0 plus 1 is 1. 2 to the power of 1 is 1. Right, 2 to the power of 1 is 2. Negative 1 times 2 is negative 1. Negative 1 plus 2 is positive 1. Okay, now, before I continue, let's make some observations here. First of all, a is less than 0. So we're going to be below the horizontal asymptote. I notice that b is greater than 1. So that means we should be getting further from 0. And I notice here that I should expect the horizontal asymptote to be one such that f of x is approaching but never is going to be equal to positive 2. Let's see if that's what happens. So far, it seems to indicate these seem to be getting closer to 2. I don't know, though. Then again, maybe that's not the case. So I plug in 1. 1 plus 1 is 2. 2 squared is 4. 2 times 2. Negative 1 times, negative 1/2 times 4 is negative 2. And negative 2 plus 2 is 0. So again, 1 plus 1 is 2. 2 to the power of 2 is 4. Negative 1/2 times 4 is negative 2. Negative 2 plus 2 is 0. Now I plug in 2. Okay, 2 plus 1 is 3. 2 to the power of 3 is 8. Negative 1/2 times 8 is negative 4. Negative 4 plus 2 is negative 2. And let's just do 3. 3 plus 1 is 4. 2 to the power of 4 is 16. Negative 1/2 times 16 is negative 8. Plus 2 is negative 6. Okay, and that's basically as far as I can get. So I'll jump to negative 2 because I'll start going the other way. Negative 2 plus 1 is negative 1. Remember that 2 to the negative 1 is equal to 1 over 2, because it's 1 over 2 to the positive 1. Negative 1/2 times 1/2 is negative 1/4, plus 2 is equal to 1 0.75, or 1 3/4. Okay, so let's graph it out. I'll do the graph in blue. 0, 1, 1, 0, 2, -2, 3, -6, okay, -1, -1.5, -2. So you can see the trend here. As we continue to get more negative, we're going to be getting closer and closer to +2. Now, if I was to plug in -3, I would get negative. I'd end up with negative 1/8 plus 2, which would be 1 and 7/8, then 1 and 15/16, then 1 and 31/32. So you can see how it's getting closer and closer. Then eventually end up with 1 and 65/535 over 65/536. So that's where we're going with that. Okay, so again, you can see a lot of these patterns continue to reemerge here. Okay, so the domain, as with before, is -infinity to infinity. The range, you can see again, we're below the asymptote. We have a downwards pointing arrow. So we should be writing -infinity, and it gets all the way, but not equal to 2. Increasing, this function never increases. It only decreases, and it decreases everywhere, and you just have to look at it to know. Okay, it's positive. So it's positive from when x is -infinity all the way to when x is 1. When x is 1, it becomes 0, and then it switches over after when x is 1 to being negative for the rest of its domain. Okay, and the y-intercept is when x is 0, and it is 0, 1. Okay, horizontal asymptote is y equals 2. Write that invisible line right there. And then the end behavior can be written in two ways, right? As x goes to infinity, f of x goes to -infinity, as x goes to +infinity, and as x goes to -infinity, f of x goes to 2. Remember, the other way you could do it technically is the limit as x goes to -infinity of f of x is 0, or rather is 2. The limit as x goes to +infinity of f of x is -infinity. And remember, the order of the statements doesn't really matter to me personally. You know, a lot of people argue you should do the -infinity first. I personally, as long as they're both there, that's fine for me. In terms of transformations from 2 to the power of x, we actually have a few here. Okay, so the negative, first of all, the negative indicates a reflection. So it depends on the order. So you can say reflection about the horizontal asymptote. Now for 2 to the x, that's y equals 0. In other words, the x-axis. So we had to reflect. We're going up like this. So this is what the parent function looks like. 1, 2, 4, 8. Half, quarter. This is what the original function looks like. So we had to reflect and come down. Okay, then we had to, and I don't want to incur the wrath of any current or former students by forgetting my arrows. So we have to reflect at the horizontal asymptote. We do need to dilate or shrink by a scale factor of 1/2 because of the 1/2 in front. And then I need to move to the left by 1 and up by 2. Folks, thank you so much for your patience. I'm just going to do one more quick one as a recap, and then we're good to go. Thank you so much. So in this last one, I've got two sequential points. And I need the equation of the exponential function that goes through them. Now, the main idea to do this is that you need to multiply. You have f of 2, and if you multiply it by b, you get f of 3, right? Because again, our idea is we want to write a function, f of x, and we're just looking for a times b to the power of x. We're not trying to do anything fancy, no h's, no k's. It's a times b to the x. And what we're operating under the assumption is that for any given number n, if you take n and f of n, its output, and you multiply by b, you get f of n plus 1, right? So in other words, if you take f of 2 and multiply it by b, you get f of 3. If you multiply f of 3 by b, you get f of 4. If you multiply f of 4 by b, you get f of 5, and so on and so on. Okay, so basically, I need a number so that when I take 6 and I multiply by that number, what I get is 4. And so that means that number has to be 4/6 or 2/3. Now to find the a value, remember you plug in a point, so I'll plug in 2, 6. So 6 is equal to a times 2/3 to the power of 2. So 6 is equal to a times 4/9. And so by multiplying by 9/4, you get a is equal to 6 times 9/4, which is equal to 27 over 2. So what you'd get as your final answer is f of x equals 27/2 times 2/3 to the x. Let's see if this works. So I plug in 2, 27/2 times 4/9. Let's see what I get. So I get 1 and 2. I get 1 and 3. 3 times 2 is 6. Perfect. And if I get 3/4, I'm good to go. If I get 3 and 4. So I do 27/2 times 8/27. And this cancels, and this cancels, and this cancels, and that for 4. Wow, okay. So everything checks out. So the idea is this: by whatever b is, if you multiply by b, you go from any f of x to the f of x plus 1. So if you were given 2 and 4, multiplying by b squared takes you from 2 to 4. Multiplying you by b cubed takes you from 2 to 5, and so on. That's the magic there. So thank you so much for tuning into this video. Hopefully you found it to be helpful. Folks, keep with it. I'm so excited to see you at the Hangout tomorrow. Have a wonderful day, and I'll see you next time.